keep going with silicates. There shouldn't be that many slides left for silicates. So as soon as that's done, we'll do a bit more speed dating and teach each other or remind each other. Before we move on to the application of silicates, let's just go over what we talked about through the intended student learning. So writing a formula of the anion in a silicate or aluminum silicate given its formula of your remember that. So write the formula for an anion in a silicate or aluminum silicate given its formula. I'm just looking at, oh sorry, I didn't turn on this. I'm only looking at the second page, second slide, sorry. Just going over intended student learning. Second one was identify SiO4 structural unit in a diagram. You just have to find SiO4, so it should be easy. Third one, draw the repeating unit and write the formula for extended silicon anion, given its structural formula. As long as you can use square brackets to identify what's the repeating unit, should be all good. State the charge on silicate anion given the Si2O ratio. The oxygen is always -2, silicon is +4 in silicates. So as long as, again, count oxygens which still has got charges, that's done. Write the formula of a silicate mineral given the structural formula of the silicate ion and the metal ions present. Metal ions can be seen on the left hand side. That was pretty common. As long as you know those charges, you should be able to find out the charge on the anion. Yeah. On the next slide, state the charge of an aluminum silicate ion given its structural formula. You're just replacing one or two of the silicons with aluminium. That's it. Explain how cations held on the surface of soil silicates and they are made available to plants. Alright?
Yeah.
Okay. So clay particles, usually negative, and metal ions will be adhering. That's what we were saying before. Describe the effect of acid rain in releasing cations from soil silicates. Yes?
This topic is very similar to like the other one. Yeah.
Environmental chem. Yeah. You remember me saying that the chapter topic 5 is application of everything you have learned. These topics ties in everything like organic chem, a bit of polymer science in there, environmental chem, and after this we will look at application of silicates. So that would hopefully tie in other things that we talked about before too.
Would any of this stuff in here be in our organic test?
No, not in the organic test. As long as you can work with protein and triglycerides.
Yeah.
And protein. Yeah. They are the applications of all the other functional groups that we talked about.
Yeah.
So it's just extension,
Yeah.
application of it. Yeah.
No.
Okay. Acid rain, releasing cations from soil silicates. So leaching is something we talked about in environmental chemistry, and that's again repeated, but from soil perspective. Second last there, explain the use of aluminium ions in flocculating clay particles. We're gonna start from there. And explain the use of silicates in water softeners. So today's lesson are gonna be all these last two really. Okay, so going to application number 2, flocculation, which is slide 27. I don't know what page that is. 14, thank you. Okay. So flocculation, something that you heard from Mr. Cook from SA Water. And also, well, we didn't get to see, but at the Bolivar wastewater management site, after the lagoon, there's a place where they make water that's in the lagoon into recycled water. So that will be sent out to like oval here or Mawson Lakes area. Yeah. And the recycled water needs to be fairly clean. Okay. Before they do that, they use flocculation. How does it work again? Well, let's look through. So clay particles, they're small enough to be classified as colloids. Do you remember what it means? No? There's a definition. Colloids stay suspended in solvents and individual particles tend to repel each other. Therefore, you would have a solution which has got a color, like everywhere you look at, you would be able to count same number of particles floating around. Okay? They're not big enough, so they wouldn't settle at the bottom. Yeah? So they will be still floating around. Milk, you don't see, fat content of it, don't sit at the top unless you do something to it, unless you add like lemon or make curdle with it. Yeah? So all the oil particles in milk, they are all suspended throughout the solution. Yeah, that's colloid. So milk is a colloid. You can maybe even say chocolate ganache is colloid, because again, I think it's the other way around. The water is floating around in oil. Okay. Okay, filtering will not remove the colloid. So what do you have to do? You would have to do flocculation. Addition of a solution of aluminum sulfate flocculates clay particles suspended in water. I should pull out a video of it, not video, pictures of what happens after the lagoon. But yeah, they do flocculation. Hello.
Hi. So it won't filter. You can't filter it because it's too small.
Too small, correct.
Yeah,
Once you do flocculation, you can.
Yep.
All right. Okay. So clay particles are negatively charged. And we established that because metal ions can adhere to it usually, right? So if you add aluminium ion, okay, they can attract those clay particles. And if the size of the flocks become bigger, what happens? They would. What's the process? So aluminium is added to the solution. It starts attracting clay particles, and then clump together, becomes big, and then what happens? Go to the bottom. What can you do with it?
Scoop it out.
Scoop it out, or filter it out, or yeah, you can do a physical process from there. Okay. Filtering will now remove these particles. Okay. So that was application number 2, flocculation. So clay particles property can be used, which is negatively charged usually. Now, water softening. You would be, already ahead of everyone, I guess. Water softening also can be done if you used certain silicates. Okay? Hard water, they contain magnesium or calcium ions. All right. So taste bitter. You would even taste a bit metallic when you taste some groundwater. Okay, if you didn't do anything to it. They would precipitate if you add soap into it. And we will talk about this soap scam in the scum. In the I have problem with scam and scam. Anyway, we'll talk about that in 5.3 subchapter. Scum. Now, water softeners, they remove these ions by cation exchange process. Now, remember the cation exchange that happened on the surface of clay? The calcium or sodium, whatever that's necessary for plant, is usually attached to it. Yeah. But if there was say acid rain comes in, they would displace. That's right. Same thing can be done, but in a better way, okay? Because water softening can be done with it. Well, I'll explain this diagram here. If you had water which has got a lot of calcium and magnesium ions in, right, and you come through, and if you had this kind of resin here, which naturally has sodium ions. Okay. Now sodium wants to be ionized, whereas calcium and magnesium can adhere to it now. So as the water goes through this resin or filter of the silicate, okay, what can happen is water only having sodium ions. Right? Now, if there was too much of the sodium, could cause an issue, but at least it's drinkable, tastes much nicer, and it's not hard anymore. Which means you can do washing with soap or less harsh detergent. All right. One of the silicates that you can use is called zeolites, and then that's something that's introduced in stage 2 chemistry course. So yeah, talk about that. It is an aluminosilicate clay. Okay. That has got a lot of open structure, so it's porous. How is it helpful? Why is it helpful if it's got a lot of pores or open structure for water to pass through?
More surface areas.
Well done. That's it. So if you've got more pores, yes, there are a lot more surface area for calcium, magnesium ion to be captured, and sodium to be released. Okay. Initially, the surface of the zeolite hold on sodium ions, and that's what it looks like apparently. Zeolite. So yeah, if you look at microscopic view of it, or atomics at the atomic level, you would see that the structure has got a lot of holes there. Okay, and sodium ions are usually attached to it. When hard water processed through the zeolite, the magnesium ion and calcium ions, they displace the sodium ions because they have a greater positive charge and they want to adhere to zeolite. So cation exchange, where did the arrow go before? Can be seen there. Water is now considered soft, and as there is no longer contain ions that will precipitate with salts. Again, that's a very good property of it. Is that the last slide? Yay. So zeolite, when you are treating water, to soften it, hard water comes in, same thing will happen, and the water would only now contain sodium. Now, zeolite is some physical matter, so that would start, clogging up, or sodium that's in there would be used up if you don't clean it or flush it backwards. And that's what happens if you want to recharge or regenerate the sodium into zeolite. You do back flushing, really. Okay? Brine solution, so salty water, would be pushed through from the other way, and then water from containing calcium and magnesium, so the hard water would come out and you would probably take it away or use it for landfill or something. So you can use this column again. So that's a process that could be used. I'm not sure how effective that is for like small communities, but that's something that could be used to soften water. All right.